Yeah, hello everyone, and thanks again for reaching out to me. And I'm so honored to be invited to present my work here. And thank you all for attending. Today, I'm going to focus on the resilient target tracking paper that you are interested in. After that, I will give a short introduction of the risk-aware multi-robot coordination. That is also a very hot topic these days. And I don't think my slides can take 2 hours. So if you have any questions, feel free to interrupt me at any time. All right, let's start. So today, robots are already helping humans to automate some dull and tedious tasks, such as these robot arms, collaborating with each other in the car manufacturing, and the warehouse robots are picking and packaging orders. So as you can see from these videos, these robots are operating in the controlled environment. So they are restricted to move to specific locations in the factory. So even though multiple robots are collaborating with each other, but they are under very, very constrained settings. So what I'm interested in is that robots are performing in the natural unstructured environments. For example, these UAVs are flying in the air for the crop monitoring and fertilization. So this is also called the precision agriculture these days. And these ground robots are delivering food in the campus. And also the video at the bottom shows the robot swarms are performing reconnaissance in an interactive urban grid scenario. So not surprisingly, in these natural and unstructured environments, we need to deal with more difficulties and challenges. So for example, we need to worry about the robot perception and the uncertainty from the environment. So the noisy perception and the uncertain environmental conditions can usually put the robot performance at risk and cause some safety issues. So also compared to this controlled environment where all robots can either talk with each other or communicate with a central server, in these unstructured environments, the communication quality cannot be always guaranteed. So there are many, many other challenges, such as the privacy issues that robots may share sensitive information. And among all these challenges, I will focus on the safety, uncertainty, and the communication. So for example, there are many safety issues, such as the robot collision and failures. The left figure shows that the accident of the self-driving vehicle in Arizona. Also, if the robots are performing in the adversarial environments, such as for military surveillance and reconnaissance, they may get attacked. These attacks from the counter UAV systems can block or compromise the sensors or the cameras on the UAVs, or just make this UAV fail completely. The safety issue can also be caused by the noisy perception. So for example, the sensors, the robots are typically noisy and have a very limited sensing range, which makes it hard for the robots to avoid nearby obstacles when the robots are moving very fast. So the limited sensing range also means in general, a robot may have local information and can only plan over a short time horizon. So sometimes the situation can be even worse. The perception can be misleading. So for example, the figure on the right shows that the GPS signal on the drone is spoofed so that this drone flies off its desired path. So in addition to signal spoofing, the communication can also be spoofed or jammed. So this left figure shows that the jamming attack on a smart parking. You can see the attacker is jamming the communication between the sensors deployed at the parking slot with this Zhou side unit, so that this controller, the Zhou side unit, is not able to schedule the suitable parking for these vehicles. And also, when the robots are performing in the field environment, the communication is not always stable and reliable because of the limited communication bandwidth, communication delay, and noise. Well, sometimes the communication can be a significant source of energy consumption, especially when the robot team has many small robots and the robots need to communicate over very long distances. So to overcome these challenges, my research focused on designing planning algorithms for resiliency, risk awareness, and parsimonious communication to save communication costs. So instead of individual robot planning, I focus more on the team level coordination and the planning strategies that give the hard guarantees with formal proofs. So for example, even though some robots in the team are malfunctioning, my coordination strategy can still give a good team performance with a hard guarantee. And my high-level team coordination and planning strategies can be complementary to the low-level controllers embedded on the robots. So most of my research are motivated by the scenarios where robots are collaborating with each other to collect data in the environment. So for example, these drones are coordinating with each other to maximally cover the wildfire in the forest. So along with the coronavirus, this wildfire is another disaster this year in California and some part of Australia. So similarly, the underwater vehicles are jointly searching the ocean floor. Also, as shown in the video on the right, these UAVs use the downwards facing cameras to track the targets, such as animals or wildlife on the ground. Among these three applications, I mainly focus on this target tracking case. So we consider a multi-robot target tracking scenario where each robot has a tracking sensor, for example, a downwards facing camera. And this camera can identify a number of the targets on the ground. So here we use the colorful dots to show the footpoints of targets. So you can also see that each robot has a set of candidate trajectories from which it can choose one to follow to cover some targets on the ground. So this is the natural constraint because at each time step, each planning step, the robot can only choose one trajectory to follow. So as we can see from this figure, robot 1 has 3 candidate trajectories. It chooses trajectory x11 to cover targets T2 and T3. And robot 2 has 4 candidate trajectories. It chooses trajectory S22 to cover targets T1, T2, T3, T4. So we can see that these two trajectories jointly cover 4 targets instead of 6 targets because these two trajectories have the coverage overlap here, the targets T2 and T3. Right? So because of this coverage overlap, the objective function, that is the number of the targets covered, turns out to be a submodular function. So the submodular function is defined on the set, such as a set of robot trajectories. And the main property of it is that it has a diminishing returns property. So for example, adding a new element E into a smaller set A can contribute more to the function value than adding this element E into a larger superset B of A. So here, like B is a superset of A. So this marginal gain means the new contribution to the function value when adding an element into the previous set. So for example, when selecting a trajectory for each robot, we consider the number of the new targets covered. So this sum-modular function is a generalization of the commonly used linear or modular function. So I think we all know that for the modular functions, the contribution of all the elements can be added up directly. Well, in this sum modular function, we cannot simply add the contribution from the individual robots because their contributions can have some overlaps. So to make it clear, let's see an example to show the sum modularity in this robot coverage problem. Similar to the target tracking case, so here you can see each robot has the camera that covers a certain area. Now we are going to deploy a new robot. Let's see what is the sum modularity in this case, and what is the sum modularity when we add a new element into the previous set. So deploying a new robot R prime covers more new area after a smaller set of robots R1, R2 is deployed than after a super set of robots R1, R2, R3 is deployed. So because the coverage area of this new robot R prime has less overlap with the area covered by this smaller set of robots. So which captures the diminishing return properties of the sum modular function. That is, adding a new element into a smaller set contributes more to the function value. So okay, so given the function is sum modular, the sum modular maximization is to select a set S with some constant that can maximize this function value. For example, in our target tracking case, we would like to select a set of robot trajectories. Each robot selects one to maximize the number of the targets covered jointly. And this problem has many applications in robotics, such as this sensor placement, where we would like to place a set of sensors to maximally cover the environment. So you can see that this coverage region of different sensors have some overlap, right? So typically in this problem, the number of the sensors that we can place is limited by some integer, k. Also, like in the environmental exploration and information gathering problems, the robots are jointly maximizing the information collected. Unfortunately, this sum modular maximization problem is generally NP hard. So which means there is no polynomial time algorithm that can give the optimal solution. Or this kind of algorithm hasn't been found. But the good news is that there's a well-known greedy algorithm that runs in polynomial time and can give a suboptimal solution. So this algorithm is actually pretty simple, and it incrementally picks the element with the maximal marginal gain to maximize the function. So for example, in our target tracking scenario, the greedy algorithm chooses the trajectory with the maximal number of the new targets covered for each robot sequentially. So generally, this greedy algorithm can give half approximation of the optimal strategy. because we know finding these optimal strategies generally runs in exponential time and is not efficient. So for example, if the optimal trajectory covers 20 targets, if we use greedy algorithm, it can cover at least 10 targets. That is half approximation. And more precisely, by using the curvature of the sum modular function, the approximation ratio is 1 over 1 plus kf. So the curvature measures how far the sum modular function is from the linearity or the modularity. So for example, if the curvature is 1, this function f is a modular function, which means that the joint contribution of the team is the sum of the individual contributions. So when the curvature is 1, is 0, the function is a modular function. And now we can see that this ratio is 1, which means that the greedy solution is the optimal solution. But when the curvature is 1, we can see that the greedy give 1 over 2 approximation. So we can see that overall the greedy algorithm can guarantee at least half approximation of the optimal. And it is the best known polynomial time algorithm for solving this sum modular maximization problem. However, the greedy algorithm may not do well in some cases. For example, there exists an adversary that can attack some robots to either block or compromise their tracking cameras, or just make the robots fail completely. So as I already mentioned, there are some companies that develop these counter UAV systems and use either laser attack or the microwave attack to take down these UAVs. So if the robot is attacked, it will stop contributing to the function value f of s. So in this case, can we still guarantee half approximation performance by the greedy algorithm? Unfortunately, the greedy algorithm can do arbitrarily bad in this case. For example, we would like to deploy 3 robots to maximally cover the targets. So here the targets are modeled by an importance map. And we assume that the targets in the darker blue region are more important than the targets in the lighter blue region. So now let's see how greedy algorithm deploy robots in this case. So we know that the greedy algorithm will incrementally deploy a robot into a location which has the maximum new coverage, right? So in this way, it can avoid the coverage overlap to increase the joint coverage performance. So the greedy does this job very well without the attacks. However, when the robot that covers the most important region is attacked, you can see now the team coverage performance decrease sharply, right? So which means the greedy algorithm is vulnerable to the attacks. So we may consider a resilient strategy to deploy robots so that they have some coverage overlap over this most important region. And in this case, even though some robot is attacked, the coverage performance is not changed that much because the remaining 2 robots can still cover most part of this important region. So here we have the main claim that we actually need some redundancy or need some overlap to counter the attacks. And so more formally, we consider this max-min optimization problem where an adversary attacks a fixed number of alpha robots in the team of n robots. So this is motivated by the scenario where the number of the UAVs, number of robots can be much larger than the number of the counter UAV systems. And we assume that only some UAVs in the team are attacked. This is reasonable because this counter UAV system is typically much more expensive than the UAV. Because like if all robots, all UAVs are attacked, we can basically do nothing. So even though we have this assumption, this problem is still very challenging because the robot team knows the attack number is alpha, but it doesn't know which alpha robots will be attacked. So considering this challenge, the robot team wants to select a trajectory set S that each robot selects one trajectory to maximize the number of the targets covered. Well, for the adversary, it wants to minimize the number of targets covered by removing a subset of trajectories A from S. So we can also see that it's like a game between the robot team and the adversary. So actually, some people also consider this problem as a Stackelberger game, where the robot team is the leader. It makes the decisions. So here, it chooses trajectory set S by considering the worst case attacks. And so the worst case attack here is captured by this minimization term. So for this attack resilient problem, we consider in designing team level coordination strategies to counter the attacks. So we first study the multi-robot target tracking with both centralized and distributed communication manners among robots. Yeah, so the centralized target tracking problem will be our focus today. And I will briefly introduce the other two. So for tracking the targets, the robot can choose a trajectory from its candidate trajectory set. And we assume that we already know the trajectory set, but in practice, it can be more complicated. That trajectory set is like a motion primitive set. The motion primitive can be computed by using the robot dynamics and the and also considering the obstacles in the environment. So then we consider a team orienteering problem where you can see that each robot can actively plan its path or trajectory to collect data in this adversarial environment. So first, in this centralized communication setting, all robots can communicate with each other to counter a fixed number of attacks, the alpha attacks. And we present a centralized resilient target tracking algorithm. And we show that it gives a constant factor approximation of the optimal and runs in polynomial time. Particularly, it runs as fast as the greedy algorithm. Let's see the details of this algorithm. And basically, it contains two steps. First, the robot team picks out alpha most valuable trajectories because recall that the number of the attack is alpha. Yeah. So in the first step, it picks out the first alpha valuable trajectories. So the valuable here means that this trajectory covers the maximum number of the targets. So for example, we consider 4 robots, robot 1 to robot 4. And these robots are tasked to track targets. And each robot has 3 candidate trajectories. So you can see the number along with this trajectory denotes the number of targets covered by this trajectory. And we assume that 2 robots will be attacked. So following the step one, we will choose the first two most valuable trajectories. So this step is going like this. So first, we select the trajectory that covers the largest number of the targets for each robot. Yeah, for example, robot one choose this trajectory that covers 15 targets, and robot two choose the trajectory that covers 10 targets, and so on and so forth. But here we also implicitly satisfy the constraint that each robot can only choose one trajectory. So then we select. Any questions? Okay. So here, like I said, we implicitly assume that that each robot can only choose one trajectory from its candidate trajectory set. So then we select the top two trajectories among all these four selected trajectories. That is these two trajectories. Because this is the top two trajectories among all these selected trajectories, right? Okay, so till now we have choosing the trajectories for robot one and robot two. That is the first step. Pick out the first alpha most valuable trajectory. So what about robot 3 and robot 4? So this is the second step of our algorithm. And in this step, we use the standard greedy algorithm to choose trajectories for the remaining two robots. So for robot 3, it is simple, and it doesn't need to consider the decisions of the previous two robots. So it just greedily choose the trajectory that covers the maximal number of the targets. That is this red trajectory. It covers the 6 targets. But the most important, most interesting part is that how to choose trajectory for robot 4. Because we know that the greedy algorithm wants to avoid the coverage overlap and choose the trajectory that can cover the largest number of the new targets at each run, right? Or for each robot. So for example, in this case, if the number of the targets covered by the red and the blue trajectories is less than the number of the targets covered by the red and the green trajectories, we will choose the green trajectory for robot 4, even though it covers a smaller number of robots. In this case, it could be possible because you can see the red and the blue trajectory have some coverage overlaps. Right? So even though the sum of the targets covered by these two trajectories is larger, the union might be less by considering the coverage overlaps. So far we have chosen the trajectories for the whole robots, and we have done our algorithm. And so our centralized resilient algorithm is the combination of this base selection, the first step, and the greedy selection, that is the second step. So the reason we call the first step as the base selection, because these alpha valuable trajectories can act as baits to attract the adversary. So because in this step, we don't consider reducing coverage overlap or redundancy because as we already saw in the previous slides, we actually need some redundancy for countering the attacks, right? But we don't want too much redundancy because if we have too much redundancy, even though there are no attacks, the performance can be very bad because you can see all trajectory overlap with each other. There is a very small contribution jointly. So for the remaining, this is why for the remaining n minus alpha robots, we use the greedy selection, and we know that the greedy algorithm can intentionally reduce this coverage overlap. Yeah, this so in total, and you can see like our resilient trajectory set is a combination of this base selection and the greedy selection. Any questions so far about this resilient target tracking algorithm?
Dr. Zhou,
Hi.
yeah, could you give us a little bit more in detail about how to allocate the targets for each UAV? Could you explain a little bit in more detail?
Yes. So I will introduce that part in the simulation, but here because in our case we focus more on the planning strategy for the robots. So for the targets, we assume that we know the GPS position of the targets, and we run the common filter on the UAVs for localizing their positions.
I mean, how to allocate the targets to each UAV. So this UAV number one tracks the which targets, and the other UAV tracks which targets.
Oh,
So
I see.
how to
Yeah.
allocate the task allocation problem.
Yeah. So here like because like each yeah, I will show that figure later, but here I briefly talk about it. So for each robot, it has the tracking region, and you can see that it has the candidate trajectory, right? And if the robot choose that trajectory, it can cover some targets on the ground. Yeah, and we like whatever what targets will be in that region is counted as the targets covered by that trajectory. Yeah, by robots following that trajectory, or more precisely. Yeah.
Okay.
Okay. So and yeah, let's move forward. Yeah, so we show that our centralized resilient algorithm gives the constant factor approximation of the optimal. So the constant factor is like 1/2 or 1/3, something like before. So you can see the approximation performance depends on the curvature of the function kf, and the number of the attacks alpha, and the number of robots n in the team. So particularly if the curvature is 0, the kf equals to 0, which means the function is modular, right? And in this case, any two trajectories from the UAVs cover different set of targets. So in this case, the joint contribution of the team can be the sum of the individual contributions because they don't have overlap. So in this case, we can see that our centralized resilience algorithm gives the optimal solution because the approximation ratio is 1. And if there is no attack, for example, the alpha equals to 0, and so if there's no attack, we don't need to consider the first step to select the alpha most valuable trajectories as base. So all we need to do is a second step, the greedy algorithm. So this is why you can see it has the ratio 1/1 plus kf, which is the same as the greedy algorithm. And this algorithm also runs in polynomial time, and particularly as fast as the greedy algorithm. We know that greedy algorithm is very efficient. It runs in polynomial time, and it is the best known algorithm for the submodular maximization without attacks. But here, like when considering the attacks, and our resilient algorithm can have the same running time of the greedy algorithm. So in particularly, it is quadratic in the number of the robots and the number of the candidate trajectories D for each robot. Yeah. So this is the simulation setting. And so to verify the performance of the centralized resilient algorithm, we run some simulations with this setting that you can see each robot has 4 candidate trajectories: forward, backward, left, and right, right? And each trajectory have a rectangular tracking region. For example, this forward trajectory has this up rectangular tracking region. And if robots follows this trajectory, it can cover these 2 targets. Yeah, I hope this can answer Nakwan's question. So also with this setting, we implement the centralized resilient algorithm into this ROS gazebo environment. So where you can see that 4 area robots are tasked to track 30 ground targets. So each robot has 4 candidate trajectories: the forward, backward, left, and right, as mentioned in the previous slide. And at each time step, it can choose one of them to follow to cover some targets on the ground. So here the cylinders are the modeled as the targets on the ground. And we assume that the 2 robots will be attacked at each round. So you can see like if the robot is attacked, for example, this timestamp, the red and the yellow, the robots are attacked, their cameras are blocked, and they will lose their tracking ability. But we assume that if the robot is attacked at the current time step, its camera can be recovered at the next time step. Because here we only focus on the one-step optimization problem. So, so to show the advantage of our centralized resilient algorithm, we compare it with 3 other algorithms. The first one is the optimal strategy, which is obtained by the brute force search, and the other 2 are the standard greedy algorithms and the random algorithms. So in the random algorithm, the robots just choose its trajectory randomly. So you can see that our resilient algorithm performs very close to the optimal solution. But we know that the optimal solution is computationally expensive by using the brute force search. The brute force search is like it enumerates all possible combinations of the robot trajectories. For example, if we have 100 robots and each robot have 100 trajectories, and if each robot can only choose one trajectory from its candidate trajectory set, the total combinations can be 100 to the power 100. That is a very huge number. So this is why it is not practical in the real world scenarios. And we can see that our resilient algorithm covers more targets than greedy and random algorithms. That is because in greedy and random algorithms, they don't consider adversarial attacks. Yeah. They just maximize the number of attacks covered blindly. So all right, that's all about the centralized target tracking. And please let me know if you have any questions. Okay, if not, I will go ahead. So in the centralized setting, all robots can communicate with each other. What if the robots have a limited communication range and can only communicate locally? So we consider a distributed target tracking scenario where robots have a limited communication range and can only communicate with its nearby neighbors. So here I use the green line to show the communication link between robots. So still we consider there is an adversary that can attack some robots to either block or compromise their tracking sensors. So in this case, we need to deal with both limited communication range and the attacks. So we designed a distributed resilient algorithm. It also has two steps. So this distributed resilient algorithm is built on the previous centralized resilient algorithm. So first, the robots form cliques based on the limited communication range. The clique is the subgroup of robots where all robots can communicate with each other. So you can see this figure shows these 5 robots form 2 cliques, and within each clique, all robots are fully connected. And also showing the clique on the right, within this clique, these 2 robots are connected. Then in the second step, all cliques perform the centralized resilient algorithm I just presented in parallel to counter attacks. So it's like a divide and conquer algorithm. First we partition the robot team into separate groups. Then within each group, the robots run a centralized resilient algorithm I just presented. Oh, by the way, can you see my cursor? Yeah, I use the cursor to point this left click and the right click. Can you see it?
No, we cannot see it.
Oh, sorry. Yeah, let me use this laser pointer. Can you see it now?
Yeah, we can see it.
Okay. Sorry about
Thank
that.
you.
Yeah. I was thinking that you can see. Oh, sorry. Yeah. So so actually, so here you can see that these 5 robots form these 2 cliques, and within each clique, our robots are fully connected. This is why in each clique we can run the centralized resilient algorithm. And we have shown that this distributed resilient algorithm also has a constant factor approximation of the optimal. So similar to the centralized resilient algorithm, the performance depends on the curvature of the function, the number of the attacks alpha, and the number of robots n in the team. So because of the limited communication, the performance also depends on the property of the graph, such as the number of the cliques k and the number of robots in the largest clique. And to verify its performance, basically the performance of the distributed resilient algorithm, we compared it with the baseline centralized resilient algorithm and the centralized greedy algorithm. In these 2 centralized algorithms, all robots can talk with each other and share information. So from the number of the targets covered, we can see that the distributed resilient performs very close to the centralized resilient algorithm, even though it has the limited communication among the robots. We can also see that the distributed resilient algorithm performs better than the centralized greedy, even though in the centralized greedy, all robots can talk with each other. That is because in the centralized greedy, the robot team doesn't consider the adversarial attacks. So in the target tracking scenario, the robot selects a trajectory from its candidate trajectory set. Can the robot actively plan its path or trajectory to counter the attacks? So the answer is yes, and we are considering a scenario where a team of robots are planning passes to monitor a marine environment, such as the monitoring oil leakage or algae bloom. And we assume that a darker color path is associated with the higher reward, such as more information collected. We also consider there's an adversary that can attack some robots in the team. So as mentioned earlier, the greedy approach tries to collect data as much as possible by planning passes without the overlap, without considering the adversarial attacks. However, if the robot that with the most valuable path is attacked, the team will suffer a huge loss. So instead, our resilient algorithm adds some redundancy when planning passes. So in this case, even though this robot with the most valuable path is attacked, the other robot can still cover most of part of this path. So the team performance is not changed that much. So we have shown that our resilient path planning algorithm can give a constant factor approximation, and it collects more reward than the greedy and the random algorithms, because in both greedy and the random algorithms, they don't consider the adversarial attacks. So actually, this algorithm is also built on the previous centralized resilient algorithm. So in the target tracking scenario, robots are under temporary sensor attacks, and they are doing myopic planning at every time step. So here you can see each robot actually plan its path with a limited budget in a finite horizon. So it is a longer term optimization problem. So this problem is also called orienteering problem in the literature. And it is NP hard even for a single robot planning. But here we design this resilient path planning algorithm for multiple robots to collect data in this adversarial environment. But we have to say that this algorithm is also an approximation algorithm, and it is not the optimal solution. So in both target tracking and the team orienteering problems, we design resilient strategies before the adversarial attacks. Now let's see how the robots can react after the attacks or failures, how the robots team can be adaptive. So we consider a team of robots jointly cover an environment. And our question is, if a robot fails, how many neighboring robots should be assigned to help compensate for this coverage loss? So our result shows that if more robots are assigned, for example, the neighboring robots within a larger help range are assigned, and the remaining robot team can compensate for more coverage loss and have a larger coverage value. However, it takes more computational time to reconfigure the positions of the robots. So basically, you can see it is a trade-off between the coverage performance and the computational effort. Okay, so that is all about the resilient coordination, what I have done before, and I'm going to talk about the second part, risk-aware coordination. So before that, any questions? Okay, so I will go ahead to the next part. So actually, in practice, even though there are no attacks, the robots may still fail randomly due to some natural events, such as the engine depletion, collision, or bad weather conditions. So this random failure generally gives the uncertainty on the system performance, or more broadly, this uncertainty can be from the unknown knowledge of the environment. So for example, these vehicles have the uncertain travel time because of the unpredictable traffic. Then the sum modular function, the objective we have studied, is not necessarily determinist, but can have some uncertainty. In other words, it becomes stochastic. So I'm going to talk about the how to design risk-aware coordination strategies to handle this type of uncertainty. So specifically, we consider a stochastic sum modular function, so which is still sum modular in the decision set S. Recall that in our target tracking case, the function is sum modular in the trajectory set. Right? But now it is the random variable, and this randomness is induced by this new parameter y. Y can represent the uncertainty in the environment. So a standard measure for the stochastic sum modular function, or for any stochastic functions, is the expectation, right? Is the average expectation. And it turns out that this expectation is also a sum modular function. So we know that if the objective is a sum modular function, we can simply use the greedy algorithm to optimize it. Because greedy algorithm is the best known polynomial time algorithm for solving this problem. But sometimes the expectation measure is not good. Let's see an example. So for example, consider two vehicles can be assigned to a demand location, and this passenger at this demand location will choose one of these two vehicles, depending on which one arrives first. So the red vehicle is closer to the demand location, but there is an intersection on its path. So if there is no traffic at the intersection, its travel time is around 10 minutes. So if there is a traffic where this is a congestion in this intersection, its travel time is around 20 minutes, right? So you can see this is the travel time distribution of the red vehicle. Well, for the blue vehicle, it is farther from the demand location, and its path is more like a freeway, and its travel time is around 60 minutes. And you can also see that its travel time is more certain because its path is a freeway. So if the passenger makes the decision based on the average or the expectation of the travel time, it will choose this red vehicle because you can see this red vehicle has a smaller average travel time. It is 15 minutes, but for the blue vehicle, it spends 16 minutes. But if the passenger chooses this red vehicle, in about 50% of cases, the red vehicle will spend around 20 minutes. Well, however, for the blue vehicle, it has no possibility of spending more than 70 minutes. So we can see that the expectation here might not be a good measure. So to avoid the risk of waiting longer at the demand location, the passenger may need to consider a better decision measure instead of the expectation. So we adopt a better risk measure from the stock portfolio optimization, the conditional value at risk. This measure is also known as CIVA. So CIVA denotes a expected performance in the worst beta-tailed cases. So the beta is the user-defined risk level or confidence level. So you can see if the beta is very small, say beta is close to 0, we actually care about the worst case scenario, right? So remember in our target tracking problem, we consider the maximize the worst case scenario. That is we consider the adversarial can be very smart to implement the worst case attack, right? So based on the worst case attack, the decision can be conservative. So in the previous vehicle demand example, if the beta is small, the passenger will choose the blue vehicle to avoid the risk, to be conservative, right? So if the beta is large, for example, beta is 1, then the CIVA measures the expectation of the entire distribution. At this, in this case, the CIVA is the expectation, is the average. So, so in the previous vehicle demand example, the passenger will choose the red vehicle to take more risk, while at the same time, the passenger can potentially get more reward. So, so you can see the biggest advantage of CIVA is that it gives more flexibility for the user to choose the risk he or she would like to take by tuning this risk parameter beta or the confidence level beta. While for the expectation, the user can only make decisions based on the average performance. So we consider maximizing CIVA instead to make the risk-aware decision. So more formally, we consider maximizing the CIVA over the decision set S. And for example, a set of robot trajectories or the set of sensors we would like to place in the environment, or the set of robots that will be assigned to the to each task location. That is a vehicle task assignment problem. So we can see that the CIVA basically measures the expected performance. This is the partition in the worst in the beta-tailed cases. So the importance of this optimization problem is that it bridges the gap between the high-level ideas of the risk awareness, trustworthiness, and the low-level specific planning for the robots. So this is new in the literature. So for solving this problem, we present a sequential greedy algorithm, which builds on the standard greedy algorithm. And we show that it gives the bounded approximation of the optimal. The bounded approximation is actually worse than the constant factor approximation because it also has the error term. I will introduce this later. And we see that the SGA runs in polynomial time because it builds on the standard greedy algorithm. So it has the same running time of the greedy algorithm. So you can see this approximation contains two parts. One is this constant factor approximation, which is from the standard greedy algorithm. And the other term is the approximation error. So just from the first part, you can see that this is exactly the same as the greedy algorithm. And this is a constant factor approximation, but we have some approximation error that is from the we need to sample the distributions from the random variables. So this is why we have this approximation error. So which makes this approximation no longer a constant factor approximation, but a bounded approximation. So this CIVA based on some modular maximization can be used in many robotic scenarios, such as this robust environmental monitoring, where the robots have the random failures. By tuning the risk level beta, the user can be either risky or conservative to place robots for the environmental monitoring. Yeah, so it can also be used in this mobility on demand case, where vehicles have the travel time uncertainty. The problem is how to assign the vehicles to task locations to get the task done as soon as possible. So this case may not make sense for the Uber service or some Lyft service, but if there is an emergency in the task locations, it can be. This is always good if you assign the more than one robot to the task location. So in other words, it's more suitable for the safety critical scenarios. Yeah, that's all about the risk-aware coordination. Let me know if you have any questions. Okay, yeah, I will move forward. So for resilient and risk-aware coordination, robots need to communicate to plan actions, but communication usually comes at a cost, especially when the robot team has a large number of small robots and the robots need to communicate over very long distances, as I already mentioned in the introduction slides. So however, sometimes for achieving a good team performance, robots may not need to communicate with all the other robots or at all time steps. So to cut off unnecessary communication cost, we designed two parsimonious communication strategies. So the first is a when to communicate strategy, where robots are triggered to communicate with neighbors only at specific time steps instead of all time steps. So we used this target tracking case. It's not shown very clearly, but here we have 6 robots. The robots can only move on the boundary of the environment. They want to track the target inside. So here the tracking is more like the estimation. Here, like each robot, the robot use the extended Kalman filter to get a measurement, distance measurements from this target, and they jointly minimize the uncertainty in the target position by sharing the measurements with each other. So here we design a strategy that each robot doesn't need to communicate with its neighbors at all time steps, and the communication can be selective. Each robot can select when to communicate with its neighbors when certain condition is violated. So we show that this self-triggered communication strategy saves more than 30% communication cost. And also it can achieve a similar tracking performance of the all-step communication strategy. So to further reduce the communication cost, we designed a who to communicate with strategy. In this multi-robot target assignment problem. Yeah. So this strategy restricts the, you can see this strategy restricts these robots to communicate only within subgroups instead of communicating with all the other robots. So the objective here is the same, and the robots want to minimize the uncertainty on the target position, but here we are considering multiple targets instead of a single target. So this is why we want to design a assignment strategy to assign a subset of robots to each target. So you can see even with this limited communication, we show that this strategy also gives the constant factor approximation of the optimal tracking performance. Yeah, all right, that's all about my PhD research, and I'm going to talk about my current research directions at the University of Pennsylvania. So the first one is also about resiliency, and is to design resilient coordination with heterogeneous information flows. So the heterogeneity here means that we consider 3 types of information flows. So you can see the first one is the organic sensing. That is the robots is sensing the environment with the sectorship tracking region or the coverage region. Or this can be seen that is a field of view of this robot. And the organic communication captures the inter-robot communication. And we also have a infrastructure, and the communication between the infrastructure and the robots, we call it as the infrastructure-based or infrastructure-enabled communication. Because here we consider that if some communication between the robots or that robot sensing is attacked or failed due to some natural events, the robot may need to ask help from this infrastructure. So that is why, like, our objective is to design resilient coordination to counter the degradations or failures in these information flows. Yeah. And we also consider the adversarial settings in this for this problem. For example, there is an adversary that can attack some information flows. For example, the attacker can attack this communication or sensing of the robots. Then how to design a resilient strategy to reconfigure these information flows for achieving a good team performance. So currently we are considering using a like model this problem as a Stackelberger game, where the team of robots makes decisions by considering the worst case information flow attacks from the adversary. So the second research topic I'm working on is to learn resilient coordination by using graph neural networks. Yeah, this is the this graph neural network is a very hot topic in the academia these days, but it may not be that hot in industry. Yeah. So here, because we have studied this robust optimization problem before, and as I always mentioned, I only give the centralized resilient algorithm, and this algorithm only has suboptimal strategies and or suboptimal performance. But by using the graph neural networks, we can learn the optimal and decentralized coordination for solving this problem by imitating an expert algorithm. This is because we can leverage some nice properties of the graph neural networks, such as the decentralized communication architectures and transferability. Because in this case, if we the transferability means that if we learn from the robot team that has a small number of robots, this learning policy can be extended or is generalizable to the large scale cases where robot team can has a larger number of robots. Yeah. This is a very nice property of the graph neural networks. So I'm also very interested in investigating the robustness of the graph neural networks over any other neural networks. So I considering that some robots where their communication links are attacked by either the adversarial perturbations or uncertainties. Yeah. So this is there's a need to design the robust algorithms with hard guarantees for addressing these issues. So basically, these are three problems that I'm currently working on. So overall, my research vision is to enable multi-robot security, trustworthiness, and long-term autonomy when robots use data-driven machine learning or deep learning techniques. So this is this captures my the application of my algorithms in a smart city. So here we have the delivering drones fly in the air, and the connected vehicles are traveling in the city for the mobility on demand. The vehicles can communicate with other vehicles, the road signs and traffic lights to managing the traffic flow to mitigate the traffic congestion. And the vehicles can gather information such as the weather and traffic conditions by communicating with the cloud, central cloud, and the nearby sensors deployed in the smart city. And our robots are executing the end-to-end actions by using machine learning and deep learning techniques. The robots can also be selective in collaborating with other robots and intelligent devices to counter cyber attacks and address uncertain environmental conditions. So another application that robots can also act as the first responders for the emergencies. Remember, like in our previous robot assignment example, we assign more than one robot to a task location if there's an emergency in that task location. And my goal is to devise algorithms to make the robots resilient to failures and plan where taking the risk of the attacks into account. To do that, robots may have to communicate with each other to replan. So this is why I'm also interested in developing the communication strategies that can be selective to save communication costs. Okay, so that's all about my talk, and feel free to ask any questions. Yeah.